Hello again. We are continuing our discussion of applying derivatives to real world situations. And today we are going to apply derivatives to one of the most common real world situations that it can be applied to, and that is motion in a straight line. So an object is moving along a number line forwards or backwards. So there's some variables we need to straighten out. The independent variable is going to be t for time, and the dependent variable is going to be s for the object's position at that time. So if the position is greater than 0 at any time, then we say that the object's position is to the right of where it started. And if the s function is less than 0 at any time, then the position is to the left of where it started. And if it's equal to 0, then the object is right back where it started. All right, so the average velocity, remember average is a secant line. It's going to be the slope between 2 points. So it's going to be s of t2 minus s of t1, so the difference between those positions, divided by the difference between the two times. The instantaneous velocity is going to be the derivative. This is where we use the derivative function, and we plug in t1. Now we use s prime as the derivative, but we can also use v for velocity, because they are one and the same. The derivative of position is actually velocity. All right, now what's the relationship between velocity and acceleration? Well, if the velocity function is greater than 0, then we know that the object is moving to the right. Where it is, that's what position tells us, but this tells us how the object is moving. And if the velocity is less than 0, then we can say that the object is moving to the left, regardless of where it is. And then if the velocity is equal to 0, then the object is momentarily at rest. It might be switching directions at that point. It might be just momentarily stopping before it continues in the same direction. All right, average acceleration. Remember, average means you find the slope between two velocities this time. So we're going to take the velocity at time 2 minus the velocity at time 1, and we're going to divide it by the difference between those two times. That's just your standard slope formula. And then for instantaneous acceleration, we're going to take the derivative of the velocity function, so v prime at that certain time, which we can also call a for acceleration. Okay, those two things will be the same. Acceleration is the same as the derivative of velocity. All right, and the relationship between velocity and acceleration is if they have the same sign, then the object is speeding up at that time. If they have different signs, meaning one's positive and one's negative, it doesn't matter which one is which, then the object is slowing down at that time. So here's an example of using position and velocity and acceleration. We have a particle that's moving in a straight line with position given by s equals 3t minus t squared, and t again is measured in seconds. So we need to find the average velocity from a time of 2 seconds to a time of 5 seconds. Then we need to find the instantaneous velocity at 2 seconds, and then we're going to figure out when is the object at rest, and remember what that means. So to find the average velocity, I'm going to take the two positions at those two times. So when I plug in 5 into the position function, I get a position of -10. And when I plug in 2 into the position function, I get a position of 2. And then that goes in the numerator. The denominator is just the difference between the two times, 5 seconds and 2 seconds. So if I simplify that, I get -12 over 3, and that is -4 meters per second. So the average velocity from 2 seconds to 5 seconds is -4 meters per second. Now to find the instantaneous velocity, remember I have to find the derivative of that position function. Well, the derivative of 3t minus t squared is going to be 3 minus 2t. Okay? And if all I'm plugging in is 2, then I will replace that t with the number 2, and I will get -1 meter per second. So at t equals 2, the instantaneous velocity is -1 meter per second. Okay, so let's figure out this last question. When is the object at rest? Well, remember, the object is at rest when the velocity is equal to 0. So the velocity, which is also the derivative of position, is 3 minus 2t. When is that equal to 0? Well, I just have a linear equation to solve now, and if I solve that, I get that t is 1.5 seconds. So the object is resting at a time of 1.5 seconds, which means it's probably switching from going to the left to the right momentarily, just at that 1.5 second mark. All right, we'll have more examples of this, but if you have any questions in the meantime, please let me know, and I will see you tomorrow.